Well, hi everybody. Welcome. We're going to be looking at statements and negation, the introduction to argument in our honors geometry class. So argument and proof is an exceptionally important part of geometric thinking in that we are going to be developing systems and structures so that we can verify every single statement that we make in class. The best kind of way to think about this is if you ever played the game Clue, you're trying throughout that game to gather pieces of evidence that allow you to deduce who was the murderer, where that murder took place, and with what weapon. So that's kind of where we're leading. So the building blocks to this are statements. Statements is any sentence which can be determined to be true or false. And the truth or falsity of that statement is called its truth value. For example, here are two sentences. Water freezes at 0 degrees Celsius. That's obviously a true statement. And 4 plus 8 equals 11. That is also a statement. We can determine that to be false, as 4 plus 8 is actually 12. So if you know whether or not that statement is true or false, it has a truth value. Here are just a few exercises. I'd like you to jot these down. We'll go over the answers to these in class when we see each other next. I want you to determine for each of these sentences, is it a statement? And how do you know? For now, you could pause the video on that slide if you'd like to take a moment. Some statements can contain what we call qualifying words. These are basically special conditions that make that statement true only in particular circumstances. The most common being some, all, and no. Now, there are some variations on this. Some essentially means at least one, but possibly more. All could mean every or always, and no means none or never. Examples being some bees sting, each square is a rectangle, and no birds fly. Some rectangles or squares means that at least one or possibly more rectangles are in fact squares. So take a moment to look at this. See if you can make these statements true by filling in one of the three qualifying words: always, sometimes, or never. So take a moment. You can pause and fill those in. Hopefully you filled them both in with sometimes. The first one is obviously trivially true. But if you filled in always for the second one, you forgot about the first prime number, which is the number 2. Additionally, if you may recall from algebra that when two variables are equivalent, we say that they are equal. Similarly, when there are two statements which share the same truth value, we say that they are logically equal or logically equivalent. Likewise, if two statements always have opposite truth values, they're said to be logically contradictory. So they're always the opposite. Here's an exercise to give you a moment to see which of these statements do you believe are logically equivalent, always sharing the same truth value, logically contradictory, always sharing opposite truth values, or could it be neither, where it's sometimes one is true and the other is false? So take a moment, pause the video now, fill that in. Okay. The first one, all pie is delicious, no pie is not delicious. You may know from English that this is the classic double negative. Those cancel out and they essentially are saying the same thing. These are logically equivalent statements. The second one, today is Monday and today is not Monday, well, that's just a single negative. So those are obviously logically contradictory. If today is not Monday, then it's not Monday. It's the opposite. Question 3 is a little bit trickier. Today is Monday and today is Tuesday. These are actually neither. Now, if you fell into the trap in saying that they were logically contradictory, consider the following 3 examples. Say today is actually Monday. In that instance, the first statement is true and the second statement is false. That might lead you to think they're logically contradictory. If today was in fact Tuesday, then the first statement would be false and the second statement would be true. Still seems like they're logically contradictory. But if today were Wednesday, both of those statements would be false. Therefore, they don't always share opposite truth values and do not meet the definition for logically contradictory. Let's look at the last example. No cell phones are in class. All cell phones are in class. This one is neither also. And if this one tricked you, it may make a little bit more sense when we look at how to negate qualified statements. So what is negation? Negation is just a process that we use to come up with a logically contradictory statement from a given statement. A negated statement always shares the opposite truth value to the original statement given, making it logically contradictory. So an example would be, my dog ate my homework. I could simply say, it is not the case that my dog ate my homework, or more simply, my dog did not eat my homework. I'm just negating the statement as given. Okay, so let's look at, well, what does that look like when we involve some qualifying words? For example, say I want to negate the statement, all bees sting. So let's presume for a moment that all bees do in fact sting. For that statement, if that statement were to be true, for it to be false, I would have to find at least one bee which does not sting. Well, at least one, but possibly more, well, that's the definition of the word some. So if we recall that the qualifying word all, the opposite of this would be at least one that doesn't, we can negate this statement by saying that some bees do the opposite. There's at least one, but possibly more bees that do not sting. Therefore, some bees do not sting. It's a little tricky. So I'll leave it to you to kind of work on why that would be the case and how to come back from it. But quickly, just for your notes, here is a summary of all of the qualified statements and their negation. The negation of some is that all are the opposite. The negation of all is that some are the opposite. Negation of no is that all are. Okay, so using that as a framework, I leave it to you to justify to yourself why that is the case. One last note is that mathematicians really hate writing out words, so we tend to create as many symbols as we can to shorten the amount that we need to write. So these qualified statements, the some, all, and no, all have a symbol in math that we use so we don't have to continuously write those words out. So for example, rather than writing out the sentence, there exists a value of x such that 2 more than x is 5, that value being 3, a mathematician would write this little backwards e symbol with a subscript x, and then x plus 2 equals 5, essentially converting the entire written out statement into mathematical symbols. This backwards e is what we call the existential qualifier. It essentially represents the entire phrase, there exists some values. So when reading it in this line, I say there exists some values, and then the subscript tells me what values I'm looking for. So there exists some values of x. The little colon means such that, sometimes written as a vertical line. X plus 2 is 5. That's exactly what this statement is saying in words. So learning how to decipher these mathematical symbols enables you to read mathematics more fluently. This is why we're talking about statements. Similarly, there are qualifiers for the words all and no. And just like for exist is a backwards E, for the word all is an upside down A. Mathematicians, you can see some patterns existing in these qualifiers. So for example, the sentence, for all values of y is greater than 4, can be represented as an upside down A with a subscript y, meaning for all values of y, such that y is greater than 4. Okay. So let's consider how we would represent the statement, no value of x is 5. Now, if you remember, we can use some double negatives here. So the word no really means the same thing as that all are not. So rather than trying to come up with a new symbol, we can use the universal qualifier or the upside down A that we've already defined to represent both words with all and words with no. So the sentence, no value of x is 5, is logically equivalent to the statement, all values of x are not 5. It's simply moving that negation from the front of the statement to the middle of the statement. And because we've rewritten it in terms of all, we can use our universal qualifier. Therefore, so we can go ahead and make the statement, all values of x such that x is not 5 is the same thing as saying no value of x is 5. Because if they're all not 5, it's the same as saying none of them are 5. Logically equivalent. Okie dokes. So, with that in mind, with these definitions of the universal and existential qualifier and what we've talked about with negation of qualified statements, I would like you to take a stab at these three exercises. I'd like you to negate each of the following qualified statements in their symbolic form. We will go over the answers to these three questions as a warm up exercise in class when next we meet. I'll see you then. Take care.